Welcome to the tinyML Asia 2020. I'm Hye-jun Ryu. I'm a professor of electrical engineering at KAIST Korea and chair of today's session, the plenary session and session number 1, hardware session. And it is my pleasure to be on the technical program committee for the tinyML Asia. It is my pleasure to introduce Professor Shouyi YIN from Institute of Microelectronics, Tsinghua University. His presentation is embedding AI in everything, deploying AI in everywhere, from a millimeter microwatt level neural processor. And Professor Shouyi YIN received BS, MS, and PhD degrees in electronic engineering from Tsinghua University, Beijing, China. And he was a research associate at Imperial College London, UK. He's a professor and vice director of the Institute of Microelectronics in Tsinghua University. Professor Yin is the Secretary General of EDA chapter in Chinese Institute of Electronics. He's also the technical committee member of Asia Pacific Signal and Information Processing Association. He has served as program committee member and organizer in the many of top VLSI and EDA conferences. He's the associate editor of several IEEE and ACM journals. Okay, please.
Thank you, Professor Yu. Thank you for your introduction. It's my great pleasure to have this chance to discuss with the tinyML. And in past few years, we have designed some very low power neural network processors. And today I want to share some results with you. So today we can see a lot of successful AI applications, such as image recognition, natural language translation, online healthcare, speech to text, and so on. However, almost all these AI applications depends on cloud computing. But I think due to some communication latency problem, bandwidth problem, or even privacy problems, in many scenarios, we can't upload all data to the cloud. So we will need a hierarchical or distributed AI computing systems in the future. And this is also the consensus of both electronics company and internet companies. Here are two figures. The upper figure is from ARM. We can see in their view, future AI computing systems should be a multi-level system, such as big ML in the cloud, medium ML in network edge, and little ML in IoT devices. And the lower figure is from Google. We can see they have some similar cloud edge systems. And therefore, there will be a big market for AI solutions on edge and IoT devices. Here is a projection about the AI chip market from 2016 to 2025. We can see more than half of this market is for edge and IoT devices, including mobile phones, smart cameras, robotics, IoT, and some consumer electronics. And when we deploy AI algorithms in edge and IoT devices, we will face the challenge of power constraints. And in this chart, we show the power constraints and the computing power requirements of some typical applications. In some portable and mobile applications, such as voice wake up for smartphone, identity recognition for wearable devices, and pattern recognition for smart sensors. Since this device has very small batteries. The power consumption must be extremely low. For example, less than 1 milliwatt. And in these applications, such as smart homes, the battery can be a little bit larger, so the power constraints can be relaxed to tens of milliwatts. And for this applications, although the power supply is not a problem, but we still face some cooling constraints. So this scenarios, in these scenarios, the power still cannot be larger than several watts. So we can see in almost all the scenarios, we face power constraints. And therefore, for the AI computing architecture in edge devices, there are three key requirements. The first one is it must be programmable to adapt to different neural networks. And second, since complete AI application includes not only neural networks, but also some classical signal processing, the architecture must be support both of these two kinds of algorithms well. And third, for edge devices, the AI chips must be very energy efficient. Typically, it should be around several to tens of tera operations per watt. And in the past 10 years, we can see there are two ways to achieve high energy efficiency in AI computing. And from the algorithm perspective, we are trying to achieve a compact neural network model so that the hardware utilization can be improved. The key techniques of achieving a compact model include network pruning, network compression, and quantization, and low-bit neural networks. And this figure shows some recent progress in low-bit neural networks. We can see battery and ternary weight neural networks has a great potential. They have low computation delays, low hardware resource requirements, and low power consumption compared to multi-bit or floating point networks. For example, the battery weight neural networks can save 32 times memory footprint. And with the progress of training techniques for binary and ternary networks, the accuracy of low-bit neural networks can satisfy a lot of applications. This figure shows the top one classification accuracy of ResNet 18 on ImageNet from 2016 to 2018. We can see their accuracy is already very close to full precision neural networks. So this extremely low-bit neural networks are not some toy. It can be used in real applications. And another way is to design some specific architecture. From 2014 to 2018, the neural network accelerators architecture evolved from application-specific instruction set processor, such as DNNs, to some very domain-specific architecture, such as low stationary data flow, sparsity-aware architecture, and flexible weight bitwise architecture. But as we mentioned before, we need to consider both neural network computing and some classical signal processing. And all this architecture are too specific for neural networks. We still need some architecture with more general programmability and high energy efficiency. And from 2015, coarse-grained reconfigurable architecture has attracted great attention. In International Technology Roadmap for Semiconductor 2015 edition, CGRA was regarded as an emerging and promising programmable architecture. And in the International Symposium of Computer Architecture 2018, the professor Kuno gave a keynote speech to show the benefit of coarse-grained reconfigurable hardware. Compared to dedicated hardware and general purpose processor, CGRA has near ASIC performance without sacrificing programmability. That's why this kind of architecture becomes very popular recently. And in Tsinghua University, we started the research about reconfigurable computing from 2006. It's earlier than ITRC report. We have successfully designed several CGRA chips for classical signal processing, such as multimedia, computer vision, and graphics. And from 2015, we employed CGRA to AI computing. Here is the architecture overview of CGRA. Generally speaking, it is a spatial architecture. The basic reconfigurable fabric in CGRA is a processing element array. And the PE array is typically a 2D mesh. Each PE consists of ALU and several local memory. So CGRA is a distributed computing and distributed memory system. And the ALU in each PE can perform multiple basic arithmetic and logic operations. So it is a general purpose architecture. It can support both classic signal processing and neural networks. Here is an animation to demo the basic principle of CGRA. In PE array, to realize a function, multiple PEs are configured to different operations and forms a dedicated data path. So CGRA has very high energy efficiency, and the reconfiguration time cost is only tenths of nanoseconds. So the function of the PE array can be changed dynamically at runtime. So it has a very good programmability. And based on the basic framework of CGRA, we designed our AI computing architecture, Thinker. It has heterogeneous PE array. In this PE array, there are two types of PE, general PE and super PE. All PE can be used for common neural computing, such as convolution layer, fully connected layer, and recurrent layers. And we also extend some general PEs to super PEs by adding some more kinds of activation functions. So here you can see the Thinker architecture has 3 levels of reconfigurability. At circuit level, the computing bitwise is configurable. And at block level, the function of each PE is configurable. And at chip level, the data path is configurable. In each PE, the computing bitwise can adapt to the algorithms. For example, a MAC unit can be split to several low bitwise MAC, which can work in parallel. So it can support flexible bitwise neural networks, especially for the low bit neural networks. It can fully exploit the computing power. And at PE level, there are several configuration bits in each PE. By configuration, the data path in each PE can be changed so that it can support different operators in neural networks. For example, if the data path is configured like this one, it can compute convolution. And if it configured as this one, it can compute full connection. And this data path is for RNN. This data path is for pooling. At a chip level, the PE array can be partitioned to several independent regions. The size of each region can be adjusted according to the numbers of layers and the number of neurons in neural networks. Therefore, different neuron layers can be mapped to different regions and be executed in parallel. So Sync architecture can support both sequential processing and parallel processing of neural networks. For example, in this complicated neural networks, it has 5 convolution layers, 3 FC layers, and LSTM layers. These neural networks can be executed sequentially. CNN, FCN, and LSTM are performed sequentially. And they can be also mapped like this. CNN, FC, LSTM can be executed in parallel. So the P utilization can be improved, and the bandwidth utilizations can be also improved. And based on the progress Sync architecture, we designed the Tsinghua processor. This is the chip photograph and Tsinghua specification. And here is a demo. Here is a demo for 2 applications, image classification and image captioning. We can see the power consumption of Tsinghua is around 400 to 500 milliwatts. And the energy efficiency of Tsinghua is around 5 TOPS per watt. So Tsinghua can cover this region. And in this region, we still need some AI processors at tens of milliwatt level. So we need to think more about how to make an algorithm and hardware co-design. By especially by some optimizations about the extremely low bitwise neural networks to reduce the power consumption. As we mentioned, binary and ternary neural networks are very small in capacity, and their accuracy is almost unaffected. So they have no multiplications in the computation, and they require low memory footprint and capacity. so they are very hardware friendly. Using these neural networks is very helpful to improve the energy efficiency. And besides these general features, actually the convolution with binary or ternary weights can be further optimized. We can see in the kernels of binary and ternary weights, there are only 2 or 3 kinds of weight, 1, 0, and -1. Therefore, in the accumulation process, there exist a lot of redundant operations, such here and here. If we can remove these redundant operations, we can save a lot of power and achieve higher energy efficiency. So we develop a kernel transformation feature reconstruction method. And here is an example. The standard convolution of this example is 64 operations. And we first transform the original kernels to new KTFR kernels. And we can see the KTFR kernels has more zeros, means they have more sparsity. And we do the convolution with these KTFR kernels with the original input feature maps, and we get to a KTFR output feature maps. And by feature reconstruction, we can reconstruct the original output feature maps. And by KTFR, we can reduce the operations to only 36 operations. So based on these optimizations, we design Thinker-2 processors. You can see Thinker-2 is extremely low power. The power consumption is always lower than 100 milliwatt. And with this face detection and recognition applications, it only consumes 10 milliwatts in these applications. And with Thinker-2, we can cover these regions. And we still need to think about those applications which needs the AI processor has lower than 1 milliwatt power consumptions. For example, in today's consumer electronics, human-machine speech interface is very prevailing. In smartphones and mobile phones, the battery capacity is very limited. So the AI processor for this human-machine speech interface must be lower than 1 milliwatt. To further reduce the power consumption, we need to consider some algorithm features in speech recognitions. Since speech is a continuous time domain signal, there are some overlapped speech feature maps which produce overlapped convolutional results. So we can exploit this temporal local data locality to eliminate redundant computing. We reuse the output of 2 overlapped feature maps at the frame level. And moreover, we consider some circuit level optimization. We find that the additions in binary CNN are dominated by 1-bit addition. So we design an approximate adder. We truncate the high-bit carry chain to shorten the critical path. And we can see this adder can guarantee the accuracy of 1-bit addition and produce an approximate result of 16-bit addition. The delay can be reduced around 50%, and the power delay product can be reduced by 48%. So with these two optimization, we designed the SyncRX processor. Here is a demo of SyncRX. It's a speech command and speech wake up application. You can see the working current is only 400 microampere. For speech application, the lowest power consumption is only 200 microwatts. That means it can enable AI processing in any portable or wearable devices. So from these three Sync processors, we can see the advantage of reconfigurable hardware for energy efficiency. Okay, finally, let me conclude my talk. If we review the progress of AI chips, we can roughly divide it into two stages. In the first stage, architecture innovation drives the energy efficiency. And as shown above, reconfigurable architecture has good programmability with higher energy efficiency. But digital architecture still face a memory wall. Therefore, recently, in-memory computing has attracted a lot of attentions, and it has shown great potential. However, in-memory computing can only support some basic multiply accumulate operations, while in AI algorithms, there are still some more kinds of operations, and we still need general programmability. So I think in the next stage, we should leverage the advantage of both reconfigurable architecture and in-memory computing to design AI chips with hybrid architecture. And I think that would be the future of AI chips. Okay, so that's all for my presentation. Thank you for your attention.
Thank you very much, Professor Yin. And we have one question. Can you comment on the specific power consumption as a function of the clock frequency? So could you comment on that? Like, for example, the IDD at 0 frequency and IDD at 200 megahertz, or like that.
Okay, so actually, if we use a high clock frequency, the power consumption will be increased. But if we talk about energy efficiency, I think the influence is very small. Actually, since we increased the clock frequency, the performance improved and the power also improved. But energy efficiency is the performance divided by power. So the energy efficiency may still stay at the similar levels. But for different applications, the absolute performance is maybe a key point. So we still need to consider the application scenario and to decide the specific of a chip. What is the working frequency and what is the power constraint?
Okay, thank you very much. Thank you very much for your nice presentation.
Thank you, Professor Yu. Thank you.
We would like to thank our sponsor again, who have made this event possible. Our primary sponsor, ARM, the software and hardware foundation for tinyML, and Edge Cortex with the dynamic neural accelerator architecture and co-exploration engine brings cloud-level performance to the edge. And Sixth Sense builds ultra-low power sensing and inference hardware for embedded mobile and edge devices. And thank our partner organizations, Shouyi as our conference partner, and all of our media partners. And you have found them all listed on our website, tinyml.org. Thank you for joining tinyML Asia 2020 with us today. We look forward to seeing you tomorrow.